Hello, hello. Okay, welcome back to our discussion on applications of IoT in various domains or areas. So now let us move to a new domain, that is energy sector. Energy sector, right? Now here we are going to see three applications: smart grid, renewable energy systems, and prognostics in energy system. Right. Now, smart grid. Now, first of all, what is grid? So, grid is your electricity generation, transmission, and electricity consumption, households. This whole structure, right, we are going to call as a grid, right? Generation, transmission, and consumption. This together we are going to call it as a grid. Now, let us see what are the problems that arises in our grid. Problem: traditional power grids lack real-time monitoring. Of course, real-time I already defined, and predictive capabilities. Right? I cannot make any future guesses or forecasting. Right? Now, inefficient energy distribution leads to wastage and higher costs, sir, because most of the times when we use right, non-renewable sources of energy such as coal, right, we have to burn the coal to generate the electricity. So when we are using inefficiently, right, then it leads to the wastage of coal, wastage of transmission infrastructure, right, and all those things, right. And also there is a cost, because everything comes at a cost. Now, limited visibility into the equipment health increases the risk of outrages and failure. Suppose take an equipment example, a transformer, right? A transformer. Now, transformer, we are not monitoring it continuously. Manually, we can't sit beside the transformer and keep on watching whether it is working or not fine. No, no, right? Occasionally visit, or traditionally when there is a problem in the transformer, when there is a power cut, we go and check, right? So this increases risk of outrages and failures, right? When we are not monitoring it, when we are it is not under visibility, right, it is the risk of outages and failures. Now, consumers have little control or feedback on their energy usage, right. Now, consumers are there. In my room, air conditioner is running, a heater is running, right. I don't know, right, how much power it is consuming, right. Is it consuming 5 kilowatt units per day, 10 units per day? If I have such feedback immediately, which I get, right, in the evening, or whenever I open my mobile app, if I see my consumption pattern, right, I can reduce my consumption, right. I will become alert, right, because I will check whether this air conditioner is consuming more electricity, right. Now, let us see the solution side. Now, we have smart grid technology that integrates sensors, communication networks, and cloud-based analytics to manage electricity more efficiently. Right. Now, it provides predictive information and recommendations to utilities, to suppliers, and to the consumers. Right. Now, smart grids collect and analyze the data on electricity generation. It will analyze, it will check the data, how much electricity is generated, how much electricity is being consumed, and what is the storage, and how much is distribution and equipment health, right. Distribution and equipment, like whole, when it is transmission, the transmission is known as distribution, right. We will be having cables, poles, transformers, various step up transformers, step down transformers. We need to monitor the health of all those equipments, right. Distribution and equipment health. What, see, suppose I would like to give an example, right. Now, at generation side, I'm generating, for example, 40 megawatt. Now, at consumption side, now if I consume only 20 megawatt, right, this leads to a wastage of energy, right. The 20 megawatt AC current, I cannot store it. I cannot store it, right. So there is a wastage of 20 megawatt, means unnecessarily I have burnt the coal. Now, if I have a information at the generation side that the consumption is only 20 megawatt, then I can limit my generation to only 20 megawatt only, right? If my consumption is 20 megawatt, generation is also 20 megawatt. If consumption increase with 30 megawatt, then simultaneously I will also start generating 30 megawatt by burning the coal. So by this way, right, if you have the information of the consumption, this information if is present at the generation side, I can generate the amount of energy required, right? How it works? Data collection, which is very important. Sensors and meters gather the information on generation, transmission and consumption, and also the equipment status. Now I will go for, with this data generated by the sensors, I will go for cloud based analysis because it is a huge data. So I generally prefer cloud based analysis. Data is stored and analyzed in the cloud for dynamic optimization of operations, maintenance and planning. I said that this generation, consumption, all this is about optimization. Right. Now suppose if some real-time monitoring, right, continuous tracking of power flow and equipment health enables quick detection of faults. Right. I will check whether how is my equipment health. Right. See, because sometimes if the equipment is not good, it consumes extra power. If the health is not good, if the health is not good, right, it will consume extra power, it won't work efficiently. It's such scenarios, what I have to do, I have to address this problem, right? I have to repair that equipment, right? User feedback. Consumers receive energy usage insights and real-time purchasing information to adjust the consumption. As I said, right, when we have insights in my home, which equipment is using, how much amount of energy, how much unit of energy it is consuming. If I have that information in real time, right, on daily basis, then I can take the necessary measures, right? If my air conditioner is, instead of consuming 2 units per day, if it start consuming 5 units per day, then I will become alert, right? Then I will go for checking what is the problem with the air conditioner, right? So all these insights I will get. Automation. Predictive algorithms optimize distribution, balance supply and demand. As I said here, balance supply and demand, right? And prevent outages. Benefits. Efficiency. Yes, of course, improves energy utilization across the entire system, right? Now, once we have all this information, when we gather and analyze data, right, where the problem is there, then efficiency automatically increases. Reliability, right, I can depend on it because it did now my system is detecting the fault at the early stage and predicts outages, reducing the downtime. Right now, if I detect my transfer is not working properly before it get damages, I will take the necessary actions. Once I take the necessary actions, then what does it do? It reduces the downtime means what? Power shutdown to a a certain area. Now suddenly transformer goes shut down, transformer damages, then what happens? During the repair of the transformer, of course there is no power supply to that area, right? So now this scenario does not happen here because earlier itself I am detecting, right, before the transformer get damages, I am detecting that it has some problem, so I can repair it in lesser time and I can reduce the downtime. Now cost saving, of course, when there is no wastage, real time pricing and optimization distributions low energy costs, right? I have given the example of air conditioner, right. Now sustainability, of course, we are dependent on the renewable form of energy, right, which is non-renewable form of energy, right? Now here coal is non-renewable form of energy. Now here, this my system helps in integrating the renewable sources of energy also, that we will be discussing in the next application. See, renewable means one which can be replenished as early as possible, right? For example, wind energy, solar energy, all those things. Whereas coal, it is a non-renewable form of energy. It takes millions of years, right, to form a coal in the earth core, right, in the mantle core. Let us, the geography is different, right, but coal, making a coal takes time, right, naturally to form, right, coal within the, it is form, right, it takes time. So once we consume all the coal, it is difficult again to generate the electricity. So what is the necessary? Here we have to integrate the renewable form of energies, right? User empowerment provides consumers with actionable feedbacks to manage energy usage. This one I said, right? Air conditioner example I have given, right? So this is user empowerment, right? In my mobile app I can see how much each equipment, how much my washing machine is consuming the energy, how much my water heater is consuming the energy. If I see that, I can take the necessary actions as a consumer. So that is, it is the user empowerment. Scalability, right? Cloud based systems allow expansion and integration with future technologies, right? So this is about smart grid. Let us go to the next application, right? In energy, that is renewable energy systems. Now what I do, right? There is a grid, there is a grid here, here there is a transmission, right? Here transmission using coal, that is thermal power plant, thermal power plant. Here using, I have solar panels. Here I use windmills, right? So I will be using windmills. I am using solar power on the transmission side, as well I am using thermal power on the transmission side, right? All are feeding to the grid, right? Now sometimes these renewable energy sources, right, like solar and wind, are variable and intermittent. Suppose there is a cloudy day. In that cloudy day, what happens, right? The solar energy is not enough to generate the electricity. There is no wind. Sometimes wind comes and wind goes, right? Their intensity also varies and their availability also varies. This variability can cause grid stability. Sorry, here it is grid instability and reliability problems, okay, or grid stability problems, however it is referred, when integrated into traditional power systems. So now what I do is, in my smart grid, right, first I feed the power using solar energy. Solar energy, here we have consumption side, right? When solar energy is not enough, right, it is a cloudy day, then I check whether the wind energy is available. Wind energy is available. Now consider a scenario where both are not available. Both are not available. In such scenario, right, I will feed the grid with my thermal energy. Thermal energy, that is by burning the coal, right? So this is the issue what it is addressed by the second point. Now come to the third point, third problem. Overproduction during peak generation periods may overload the grid, right? So now suppose all the three sources of energy I am feeding to the grid. What does it do? It lead to the overload. While sometimes underproduction, right, all the three are not available, it leads to shortages, because here I don't have the necessary information. So let us have a discussion on the solutions. IoT based systems, they are integrated with the transformers at the point of interconnection, right, where we measure electrical variables and monitor how much power is fed into the grid. Electrical variable means voltage and current. We measure voltage, current, power, all those things we measure, and we see and we monitor, right, how much power is fed into the grid. These systems provide real-time data to the utilities for decision making. I explained right this way. This example is discussed here. One simple solution to maintain stability is to cut off overproduction when supply exceeds demand. Yes, when supply is more than demand, what does it mean? It is overproduction. So now here when we have data, the data that is collected by the sensors which are aggregated in the cloud, by analyzing the data we can check out that overproduction is happening. In such scenarios, what I can do, I can cut off the excess supply. I can shut down the thermal plant, right? I will allow it to run only on the solar energy and on the wind energy, right? So Advanced solutions include energy storage systems like batteries, pumped hydros, and demand response programs to balance demand and supply dynamically. Now, how this renewable energy system works? Let us have a look of it. How it works? I have sensors and IoT devices. They measure the voltage, current, and the power flow at various interconnection points. Data is transmitted to cloud-based platform for analysis. Algorithms predict that fluctuations in the renewable output and recommended corrective actions. Right? They will check out, is there any fluctuation in the energy output? Right? Then in such scenarios, they will recommend the corrective actions. Right? For example, if overproduction occurs, power can be curtailed, that is cut off, right? One of the either solar energy or wind energy or thermal energy, you cut off from the grid and stop production there. Alternatively, excess energy can be stored or redirected to the flexible loads. Utilities use this information to optimize the grid operations, maintenance and planning. Right, let us see what are the benefits. Grid stability prevents overload and blackouts by the balancing supply and demand. Efficiency, real-time monitoring improves energy utilization. Sustainability enables high penetration of renewable sources. As I said, right, we are penetrating, we are giving the supply from wind energy, we are giving the supply from the solar energy, right? So high penetration of renewable sources without compromising the reliability. Right, now you can trust on it. Cost savings, yes, reduces wastage. Of course, when there is less power consumption, when I am not wasting the energy, of course I will not pay the bill, hence I have cost savings. Predictive maintenance, right, I can predict, right, the damages. Right, now I can, if I have a transformer, if I have data of the transformer that it is continuously, right, fed to cloud, I can monitor, right, what is the input voltage and current to the transformer, what is the output input voltage and current to the transformer. I'll keep monitoring those values. If they are deviating from the normal values, then I understand that there is some problem in the transformer, then I can take the corrective actions, right, so which avoids outages. User empowerment, right, provides feedback to the consumers on energy usage and pricing. Right, let us discuss the last applications in the energy. Prognostics in the energy system. Okay, problems. Energy systems like power grids and industrial machines face unexpected failures due to wear, stress and anomalies. Traditional maintenance is reactive, often performed after breakdowns, leading to downtime and high costs. Once the transformer is completely uh, shut down, right, it is not working. Once the transformer, right, is completely damaged, it burnt out, etc, etc, it is difficult to reimage. There is downtime increases most of the areas, power cuts. Right, now breakdowns, to keep it in simple words, breakdown means the state of not working. Right, so now lack of predictive insights makes it difficult to ensure reliability and stability. So what is the solution? Right, IoT based prognostic management system which continuously monitor equipment performance in real time. Right, then once they continuously monitor, while continuously monitoring, they analyze the deviations from the normal operating profiles to predictive potential failures before they occur. Right, for that what we have, I will explain with an example. We have a phasor measurement unit which collects the electrical data from the power grid. Now suppose t, time versus phase and phase. Right, generally the phase is constant. Right, now in certain situations the phase may increase or phase may decrease. This is the normal. Right, so here this is normal, the middle one is normal. Now these are the deviations. If there are such deviations that are occurring in our equipment, then I can predict that there is something wrong. Then I can go and repair. I can go and repair to avoid damage, and shut down. This is called as a predictive, right? This is called as a predictive insight. This is called as a predictive insight, and the same thing is called as a prognostic. Prognostic is checking out, right, checking out its symptoms before it get damaged. See, what is diagnostics? Once we fall sick, once we become ill, then in diagnosis we find out what is the cause of the sick. But here in prognostics, we find out, we predict the things before it get damaged, so that I can take necessary actions. See that, like this, right? See something. See, here it is a failure, failure failure of transformer. If here I find out, right, find out its symptoms, I call it as a prognosis. After failure, if I find out the causes, I call it as a diagnostics. So tools like OpenPDC process massive amount of streaming time series data, like predictive for predictive analysis. How it works? Data collection. Phase measurement units and other IoT sensors capture real-time electrical variables, voltage, current, frequency. These data are processed in the applications like OpenPDC, which can handle large amount of data. Analysis. Algorithms compare the current performance with baseline operating profiles to detect the anomalies, right? Like this. If some behavior is like this, suddenly there is some behavior, it goes like this, some here, the anomalies, right? So I can detect there is a problem. Prediction. The system forecasts impending failures or performance degradation. Alerts and actions. Operators receive notifications to perform preventive maintenance or adjust operations. Let us see benefits. Reduced downtime. Predictive maintenance helps in reducing the unaccepted breakdowns. Cost efficiency, minimizes repair costs and extends equipment lifespan. I said, right, if we detect the repair problems initial stage only, it's going to cost less. Reliability improves stability of power grids and energy systems. Safety, early detection of faults reduces risks of accidents and outrages. Scalability, cloud-based platforms can handle massive sensor data streams across large networks. So this is about the applications of IoT in the energy systems. Thank you.